Alright, today we're going to look through our constant velocity review. So starting off with number 1, tell a short story in words for the position graph shown. For each of the segments, mention about general speed, like fast or slow, starting position relative to the origin, direction of motion, and whether their velocity is changing or constant. Alright, so we're just going to go one by one. Let's start off, and we're going to look at this section. So here we have this constant positive slope. So I'm going to say, let's say Todd, that'll be our character, starts behind a tree and walks slowly past it. Okay, so that is our first line, right? We have this constant positive velocity. We know that because the velocity is the slope of our position time graph. Our slope's positive, our velocity must be positive, but it's not incredibly steep. That's why I added in this little blurb about how it's slow. Especially with later on in the graph, we can see it gets much steeper. Okay. Then, let's look at this middle section right here. That has a slope of 0. We know that means we're just at rest. So Todd then stops moving for a few seconds. Alright, and then, lastly, this section, now we have this downward slope. That means we're moving backwards. So Todd runs backwards until he reaches the tree. And that tree is what I'm calling the origin. So we can see in our line, he hits the origin. Right here, hitting the origin, that's where our tree is. So Todd runs all the way back until he reaches the tree. Number 2, identify the SI units for each of the following. Velocity, that's measured in meters per second. Position is measured in meters, and time is measured in seconds. Number 3, a bike travels at a constant speed of 4 meters a second for 5 seconds. Calculate the distance the bike travels. Write your givens, start with an equation, and show all work ending in an answer with units. Alright, when we're solving physics problems, I always like to start off listing off our givens. So we know, as we're reading, using our units, right? We know velocity is in meters per second. So constant speed of 4 meters per second, that must be the velocity, because its units match. 5 must be the time, because the units match. So we immediately identify velocity, we identify time, and now we have our equation. Our equation is delta x is equal to velocity times time. We can go ahead and plug in our variables. So let's plug in that 4 meters per second. Let's go ahead and plug in that 5 seconds for our time. And if we go ahead, we'll find out our answer here, 4 times 5, is going to give us 20 meters for our answer. You can see, working with the units, that these units, the seconds and the seconds, are actually going to cancel. That gives us our meters. That's why our answer is just in meters. So units work out as well. Number 4, the light from the sun reaches Earth in 8.3 minutes. The speed of light is 300 million meters per second. Calculate the distance from Earth to the sun, givens, equation, and then show work. Alright, so givens. Well, here we have time in minutes. Right here we have velocity in meters per second. We need to make sure these units match up. So if you have meters per second, our time, we should always convert to our standard units that we have right up here. So let's get that time in seconds. If we're starting off and we say we have a time of 8.3 minutes, well, what we're going to do, and we did this a little bit in chemistry, is we're just going to convert our unit. We have minutes right now. We want to get rid of minutes. So what we're going to do, take the unit we want to get rid of, and that goes on the bottom. The unit we want goes on top. We want seconds. And now we just want to make sure that this fraction is 1 over 1. So that whatever we're putting for minutes is balanced by an equivalent amount of seconds. So we know that 1 minute is 60 seconds. This is 1 over 1, right? 60 seconds is a minute. We're not changing the value or the amount of time. We're just changing what we measure it in. Now, our minutes cancels and we get units of seconds. So if we take 8.3 and we multiply, grab my calculator, 8.3 times 60, we get that time of 498 seconds. And just like in the last problem, take our equation, delta x is equal to velocity times time. We'll plug in our velocity, 300 million meters per second. We'll plug in our time. Now, again, we're just going to multiply velocity by time. This one's going to be a big number, 300 million times 498. And in my calculator, I get a delta x of 1.494 e to the 11th. What that is, that's just scientific notation. That's 1.494 times 10 to the 11th power, and of course, that'd be in meters. But what we're going to do is we're just going to round that for simplicity. That is 1.5 times 10 to the 11th meters. Now, if you're curious, writing that out, that would be, still got some more zeros here, that would be that many meters. So that is a huge, huge distance, of course. It's the sun to the earth. Let's make sure we're still recording. Lovely. Number 5, you and your friend each drive 50 kilometers. You travel 90 kilometers an hour, and your friend travels 95 kilometers an hour. Calculate the amount of time your friend waits for you at the end of the trip in hours. Again, we're using givens, begin with calculations, and show all work. We need an answer in units. Okay, so we know we're each driving the same distance. What we're going to do is we're going to solve this equation twice. Delta x is equal to velocity times time. We need to figure out time. That's what we're looking for. We can find that if we plug in the delta x and we plug in the velocity. So let's first do you, right? You're traveling 90 kilometers an hour. Here, you might ask, wait a minute, Mr. Rosauer, shouldn't we convert our units? And you absolutely could, but there's something really neat that's going to happen. Let's try our first part. We know we have a velocity of 90 kilometers per hour, and we are driving 50 kilometers. What happens when we solve this equation for time, right? We're going to rewrite it. We know we're going to divide both sides by the 90. Our units come with, right? We're dividing by 90 kilometers an hour. And now going back to algebra, you might recall that what actually happens in a situation like this is the kilometers is going to cancel. The hours gets brought up to the top. So really, our units are just going to be hours. When we do this, 50 divided by 90, our answer, that time, and what we get right here is 0.55, and I'm just going to round it to 6. That's in hours. So that's how long it takes you to make it. Let's do that same process, but figure out how long it takes your friend. And they're going a little faster, maybe a little overzealous to get to their destination. Remember to drive safe. It's an hour times time, same process. That distance divided by the velocity.
Hey, sorry to bother you. Do you mind sitting in my study hall for a second?
Yeah, I got you. Alright, let's see. Where were we? So we're just calculating the time it takes for our friend to run. We have 50 divided by 95. Let's grab our calculator. And 50 divided by 95. We get the time being 0.526. And again, that's hours. So then, I should be consistent here. I only wrote H for hours, but now we're doing HR. So let me add those in. Okay. So now, we figured out how long it takes for each person to get there. All right. Here, this is you. This is your friend. So now we have to decide the amount of time your friend waits for you at the end of the trip. Well, really, what's going to happen? Your friend arrives, and then you arrive. What we can do is just take the time that it takes you and subtract the time it takes your friend. Because your friend gets there, but you haven't gotten there yet, right? You get there in that difference of time. So this would just be 0.556 minus 0.526. And we find out, okay, they wait 0.03 hours. Alright. Now to double check we're still recording. Number 6, you and your friend are both leaving Indiana University at the same time to go to Michigan State University. You travel 65 miles per hour while your friends travel 75 miles per hour. Distance between the two schools is 300 miles. Calculate the time you spend driving in hours. Okay. So this is very similar, right? What we're going to do, you each spend driving. Okay. So for you, we're doing the same process, right? Same equation. Delta x is velocity times time. We know the velocity of u is 65 miles per hour. We know the time. Actually, we don't. This is equal to 300 miles. We're solving for the time. We take 300. And we divide by 65, and we find out the time it takes you is 4.62 hours. And then your friend, same calculations, same equation, delta x is equal to velocity times time. They're traveling 300 miles. They're traveling at a speed of 75 miles per hour. Solve for that time, and we'll go ahead and we're going to divide 300 by 75, and the time it takes them is just a nice round 4 hours. In part B, calculate the amount of time your friend beats you to MSU in hours. Well, they beat you. Again, same process we did for number 5. They beat you by 0.62 hours. Just taking the difference between the time it takes you and the time it takes your friend. Describe what a position versus time graph looks like when an object changes direction. Okay. For an object to change direction, again, if this is our position, this is our time, what that's really going to look like is it's going to look kind of like a piecewise function, right? If we do our graph, say, in purple here, and we have this positive slope, right? We're moving upward, moving in the positive direction. If that slope becomes negative, then we know we've changed directions. Now, we were moving forward, and then we end up moving backwards, because velocity is the slope of a position versus time graph. So if your slope changes from positive to negative, or negative to positive, you know that you must have changed direction. Describe what a position versus time graph looks like when an object is moving away from the origin with a positive velocity compared to a negative velocity. Well, again, drawing out a little diagram here. Here's our position versus time. If you're moving away from the origin with a positive velocity, we know positive velocity means positive slope. So that would be something like this. And moving away from the origin with a negative velocity would have to look something like this. Something to note is, with a positive velocity, to be moving away from the origin, you have to be in front of the origin, right, ahead of it. If you were, say, behind the origin and you had a positive velocity, your position time graph would look like the blue line I'm drawing. But of course that would be moving towards the origin until you eventually pass it. 9. Draw a position versus time graph of a person walking at a constant speed of 2 meters a second. Call this person A. Okay. Draw a position versus time graph walking at a constant speed of 2 meters a second. Well, 2 meters every 1 second. We're going to start at our origin. They're moving 2 meters, 1 second, so 4 meters and 2. And we can just get our nice little graph right here. I'll try to match it as best as possible. So at 12, we should be at 24. There you go. Okay. This is person A. On the same graph, draw a person running at a constant speed of 4, but 3 seconds after. Okay, we'll do this in green. So they start 3 seconds after. So they haven't moved. So at 3 seconds, this is our starting point. That's when they start moving. And they're moving 4 meters a second. So now the slope will be double. Right, we're going 4 in 1 second. 4 in 1 second, 4 in 1 second, 4 in 1 second, 4 in 1 second, 4 in 1 second. Okay. That is person B. Right? We'll label them B. I don't think it says to, but we're going to do it anyway. Besides the starting line, do the two people ever meet? Yes, absolutely. Alright, continuing where we left off. Number 10. Besides at the starting line, do the two people ever meet? Yes, they meet at 12 meters. At what time does runner B overtake walker A? Well, at 6 seconds, runner B overtakes runner A. We can see at that point, they're at the same position, at the same time, but then afterwards, B has surpassed A. So at 12 meters is the position. That's also exactly where they met. And we know the time that happens is 6 seconds. If the two people were in a 24-meter race, how much time would runner B beat walker A to the finish line? Okay, great question. What we'll do, we'll use our equation, and just like we've done before, we're going to solve it twice. We know, let's say that on the left, we're going to do runner A. On the right, we're going to do runner B. So, we know they're both running a 24-meter race. The velocity that runner A is moving with is 2 meters a second. So we'll plug in that 2 meters a second velocity. We can solve for the time by just dividing 24 by 2. And we get that time of 12 seconds. Now let's see how long it takes runner B. Something we have to be careful with is we know runner B doesn't start at a time of 0. Runner B starts at a time of 3. Right here. So whatever our answer is, we need to add 3 seconds. So, to travel 24 meters at runner B's velocity of, I believe it was 4 meters a second. Let's double check. It's 4 meters a second. We'll go ahead and grab that. And now we can go ahead and take 24 divided by 4, and we get our time of 6 seconds. Now be careful with this. Again, like I mentioned, that's how long it takes to run the 24 meters. But runner B isn't moving the entire time. Right? Runner B starts 3 seconds later than runner A. So, really, runner B is going to arrive 3 seconds ahead of runner A. Because runner B runs the distance in 6 seconds, but also waited for 3 seconds at the beginning. So runner B wins by 3 seconds. If you drew your lines really precisely, you could even read this off the graph and see, oh, at 24 meters, the end of the race, runner B gets there at a time of 9 seconds, where runner A gets there at a time of 12 seconds. 3 seconds of difference, just like we calculated. Where along the 24-meter race would walker A be when walker B crosses the finish line? Well, we know walker B crosses the finish line at 9 seconds. So we're going to say the time we're looking for is 9 seconds into the motion. We know the velocity of runner A is 2 meters a second. Let's go ahead and plug this in to our equation. Plug in our 2 meters a second, plug in 9 seconds, and we go ahead, multiply, we get 18 meters. So 18 meters is our answer. That's where runner A would be when runner B crosses the finish line. Let's double check we're still recording. Excellent. A bicyclist is moving along a straight street oriented east-west. In drawing the graph, positions to the east of the origin were marked as positive, and positions to the west were marked as negative. At time t1, is the cyclist moving? If so, in what direction? Explain your answer. Well, at a time of 1 second in, we can look on their position time graph and we see there is some positive slope. They have a positive slope. Slope of a position time graph is the velocity. So they have this positive slope, they have this positive velocity. Yes, they're moving east, because we know east is marked positive. They're moving in the positive direction with this positive slope, they're moving east. At a time of 1 second, is the cyclist changing speed? No, they're not, because the slope is the same. Slope determines the speed, the slope's not changing, the speed is not changing. At a time of 9 seconds, is the cyclist moving? If so, in what direction? Yes, they are still moving. And they are still moving at the same speed that they were at a time of 1 second. They are moving east. It's the same slope at each point in the graph. No matter where you mark it, they're moving at that same velocity because we have one slope. At a time of 9 seconds, are they changing speed? No, they're not. Again, it's a constant slope. At a time of 4 seconds, is the cyclist moving? Yes. They are still moving east at the same speed they were at 1 second, at the same speed they are at 9 seconds. When we're on our x-axis here, that doesn't mean we're not moving, it just means we're at the origin. Are they changing speed? No. The same story for all of these. Because the slope is constant, they are not changing speed. Alright, last question by the looks of it. Two runners approaching each other on a straight track have constant speeds of 4.5 meters a second and 3.5 meters a second, respectively. When they are 100 meters apart, how much time will it take for the runners to meet, and at what position will they meet if they maintain these speeds? Okay, really, there's a couple ways to solve this problem. One way I'd like to present is to draw out a picture. I always recommend drawing a picture for really any more complicated problem like this. It might even help to draw out a position time graph. We know that one person, they're starting, and we're just going to draw out a qualitative position time graph. One person's starting at 100 meters. The other person, we'll say they're starting at the origin at 0. And they have these constant velocities. Eventually, their paths are gonna, let's draw that as a better line, they're gonna intersect. And wherever they intersect, that is where they meet, at what time they meet, and where exactly they meet. Let's say our person that starts at 100 meters, they're moving at that velocity of 3.5 meters per second. And in particular, this is a negative velocity. They're moving downward. person moving forward, they have that velocity 4.5 meters per second. It's positive because they are moving forward in the positive direction with this positive slope. What we can do is we can actually write out an equation for their position. We know that the equation for an object's change in position, their displacement, is the displacement is equal to velocity times time. Displacement is how much they change their position. We mentioned how you can always get the final minus initial for a change in position, right? The change in position is going to be your final position minus wherever you started. If we rearrange this, what we see is that the change in position plus your initial position is just going to equal your final position. So what we can then do, right, the position we're looking for is that final position. We can say, substitute in velocity and time for your displacement. And then we can say, well, velocity times time plus your initial position gives you your final position. So for the person starting at a position of 0, right, their initial position is just 0 meters. Their velocity is 4.5 meters a second, and we multiply by time. That gives the final position. For our other person starting at 100 meters, well, their initial position is 100 meters. Their velocity is 3.5 meters per second. What we want to do is we want to set these final positions equal to each other. Now, with this, all we'll do, right, we'll just plug all of this in for our final velocity, right into our equation right up here. So what we end up getting is, and we'll do this in purple, we get 4.5 meters per second times time is equal to 3.5 meters per second times time plus 100 meters. Something we want to be careful with is the velocity here for our person that's starting at 100 meters. It needs to be negative. So when we write out our final equation, this should be negative. Now we can go ahead and solve. Let's add 3.5 meters a second to both sides. That gives us 8 meters a second times time equals 100 meters. Divide by the 8. 100 divided by 8 is going to give us a time of 12.5 seconds. This is going to be our passing time. Now to find out the location, we just have to take that time and plug it in with one of our velocities. So take our delta x is equal to velocity times time. The passing time is 12.5 seconds. That's when they're at the same location. Plug in a velocity of 4.5 meters per second. Multiply those, and we will get the displacement of that object moving at 4.5 meters a second, the one that starts at 0, to be 56.25 meters. This is the distance from your 0 position. Alternatively, there is a different way to solve this, and some of you solved it this way when we were doing similar problems on our whiteboard. What you can do is, since the two objects are approaching each other, I like to draw out a little picture. Right, we have one object that's moving 4.5 meters per second. The other one is moving negative 3.5 meters per second. They're moving towards each other. This distance between them is shrinking. And it's not shrinking at the rate of just one of them moving. Right? If only the object on the left was moving, the gap between them would shrink 4.5 meters every second. If just the object on the right was moving, the gap between them would shrink 3.5 meters every second. Since they're both moving towards each other, the gap is going to shrink at those rates combined. 4.5 meters every second plus 3.5 meters every second. If we add those up, right, 4.5 plus 3.5, we see the gap, the distance between the two objects, shrinks at 8 meters every second. We know the distance between them is 100 meters. It closes at 8 meters per second. If we take 100 meters and divide by the rate the gap is closing, 8 meters a second, we can find out the time. And we get that exact same answer for the time, just like we did up above. Two different ways to solve it. One might be slightly harder than the other. If you understood the first way and that makes sense, absolutely stick with that. If you understand the second way and that makes more sense, absolutely stick with that. Go with whatever makes the most sense to you. For extra review, make sure to practice your problems that are in our problems packet. You have the answer keys. You can always go back and just double check. Make sure you're confident in all those different aspects.